Hackett. This is Ashley, Laura, Leah, and Lukesh. Okay, so this is what we're thinking of. This is our tube to propel, and we're gonna have to cut it and shorten it. Yeah. Right here is like this device in order to kind of have to put it on an angle, and we can write down what each angle is, and this way this will be attached somehow like this. Want to get a better, closer look, so that we can move it basically up and down, and we'll have it attached to like a base, like a block. Then this is the spring that we're using, which is like pretty compressible, and it fits perfectly into this tube. And we're either going to use elastics or something in order to actually propel the object.
A string in the slits, right?
Yeah, we'll bring it down.
To pull it down.
And then it'll go back up and shoot through the...
And we'll calculate the initial velocities based on experimentation. With
the
X values of distances and times. And different angles that we are known, yeah.
Alright.
Alright, so that's it for now. Thank you.
Yeah.
Hi, Mr. Hackett. So this is November 8th.
Friday,
November 8th, and we just spoke to you. And so what we decided is that we were discussing our catapult project, and we were just going over a few little topics. So, for example, how this is a bit heavy, and how we can't compress the spring too much, or else it won't go back to its natural position. And also maybe perhaps contemplating having a see-through tube, but we're going to see if we can actually find that. We'll look into it. Otherwise, we can do all of our calculations and using by having our angle. And with that, we can also find our K constant for the spring, and then we can even find what the greatest angle is if we wanted to, of projection.
Yeah, Peter, yeah.
Oh yeah, so now we're going to cut this. We're going to cut it quite short, so that there's as little friction as possible in the tube with the ball. I'm probably going to be using around a marble to project this. Oh, and we're going to be using a piece of wood right here. So we're going to be using wood in order to keep it upright and to stand still with this tube, and it'll then be able to move, and that'll just be like our whole base of the project, and then we'll use it. Right, we'll nail it in here into the wood. Okay, so now we're going to go and cut our tubes and start putting it together. Woo! I'm Mr. Hackett. So it's Friday afternoon, and we came to my house after our lab period. So as you can see, lots of progress has been made. Okay, so right here is our catapult. This is still the same spring that we were using before, and we put this little piece of almost like styrofoam thing so that our marble won't fall through the spring. Okay, so now we have our tube. We've cut these two slits here on either side. There's one side here and one over here. Inside of it, so that the spring will only fall up to here into the tube. We've placed this extra barrier. It's actually another tube that's been inserted and screwed on. So we made a few changes to our idea. Like, instead of using this big piece of metal, we just decided to screw it on with a basic screw that we can just unscrew and then
to adjust the angle.
Yes, in order to adjust the angle, which goes up and down. Okay. So should we
have a range of 25 to 90 degrees.
Mm-hmm. Yeah.
Because it doesn't go flat down.
Yeah, not all the way.
We also changed the idea of the strings, so we're just using this instead, and we're gonna get a new one so that it's smooth. This is just to try it out. So
here's a demonstration.
Alright, so I'm gonna back up just. So you can't see it very well because it's kind of a marble and but it did go kind of far.
And that's at the lowest angle.
And that's at the lowest angle. If it were to go at 45, it would probably go much further.
But that's a good range.
that was
Yeah,
really good.
it's a good range. All right, so yeah.
That's it. Thank you.
Okay, so we're doing a comparison between a calculated value for theta versus the actual value that we measure on our protractor. And we're doing this by measuring the horizontal distance, the vertical distance, time, and with our known value of acceleration, and solving for theta.
And we're just going to mention that we're not going as hard as we can with using not much force, because or else it goes really far.
Yeah, try to get just a better value. Hi, Mr. Hackett. This is Laura. It's November 25th, and we have finally done the final finishing touches on our project. While my teammates are editing the video and also finishing the report, I have just added the final details to our catapult. So one of the first changes was the addition of our protractor. As you can see, it's placed right here. It's a bit distance from the rotating angle, and it is completely centered with our pivot point right here. This pivot point goes directly through the center of the tube, so we know that it is right in the middle. And as well, the 0-degree angle is perfectly aligned with the wood. So this means that it is properly aligned and we'll get an accurate angle when measuring. The second change was that we used this metal rod, which is much thinner and smaller and is not indented, so it doesn't cause friction, instead of the previous one which we were using. We did contemplate using strings, however the strings would get stuck into the spring when it was being shot, and also there was nothing preventing the spring from shooting right out of the PVC tube when we used strings. So we didn't use that, and in the end we went with this, which was lighter and more efficient and better. Lastly, we just added these styrofoam pads at the bottom. This just is in order to stop the friction and to stop this from sliding, which it was doing a lot of beforehand. And for pretty details, we added our name. Also, when someone would be doing the lab, we'd also have to take into account how the catapult is a certain height higher than the ground level, and that would be important. One last detail was the addition also of this ruler, which is put right onto the PVC tube so that we can measure the compression of the spring when it's shot down.